My name is Charles Makel from Argonne National Laboratory, and I'm going to be talking about an equivalent recursive system for general agent-based models. In this presentation, I'm going to formulate what I call the general agent-based model as a nested recursive function using the Mathematica and Wolfram language. And we will demonstrate the nested recursive function for an example agent-based model, which is the so-called SIR epidemiological ABM. The SIR stands for susceptible, infectious, and recovered, which is a common model that we've seen and used extensively during COVID. So it relates to that as well. First of all, recursive systems. A recursive system is a function that is solved recursively with the result of one iteration of the function used as input into the next iteration of the function. So Stephen Wolfram did some extensive explorations in deterministic recursive systems and showed that such systems can produce a range of complex behaviors, including apparent randomness. He's done a lot of recent work on this in 2024, last year, but the origin was extensively covered in the book A New Kind of Science. So I came across Stephen's video and blog actually on recursive functions, and I was extremely intrigued and interested by the simplicity, I would call it, of such a formulation that could produce incredibly complex behaviors with the right parameter settings. Okay, first I want to explain what an agent-based model is. An agent-based model is a computational model for simulating the actions and interactions of autonomous agents, who could be both individual agents or collective entities. Such as organizations or groups, in order to understand the behavior of a system and what governs its outcome. Agent-based modeling has achieved widespread application for simulating many conceptual and realistic socio-technical systems that contain a human element. And the key feature of the human element is to include behaviors or decisions that agents make. Typically, it's we want to include the human element actually in such simulations. A typical usage for agent-based modeling is to simulate artificial societies in which agents are individual people that have autonomous behaviors, interact with each other, as well as with an external environment that's outside the agents and collections of agents. So there's been many applications, both in scientific literature to really understand how systems behave with the human element included. And there's been also many practical applications, everything from modeling, the stock market, and including behaviors of individuals in the stock market and their trading decisions, to such things as modeling consumer markets, consumer behavior, reasons for choosing and selecting particular products based on their characteristics, as well as the characteristics of the individual agents or people making those consumer decisions. In any agent-based model, there's 4 essential elements, and this covers every agent-based model. Recently, I've been on a quest to distill and simplify the elements of any agent-based model, and here they are. Basically, we have a set of agents. Agents could be people, they could be robots, they could be animals who we're trying to model the habits of, things like that. Agents have attributes, which are basically characteristics. So an individual person might have characteristics such as their age, race and ethnicity, gender, things like that, that are key to the kind of decisions that people make that we want to model. Agents also have behaviors, and essentially a behavior is just think of it as a function that operates on an individual agent. And there's some kind of outcome of a behavior, either an action by the agent or maybe some kind of change of state of the agent. Could be something that's the agent state may change by just adding something to its memory. It doesn't have to actually act. Or it could be a change in its basic feeling about something. Number 2, a set of agent interaction groups. So the key aspect that really defines agent-based modeling is the fact that groups of agents interact with each other. That really complicates how one goes about modeling agent-based systems. Okay, third, everything else that's in the model that's not part of the agents goes to the environment. So for example, if we're modeling things like farmers in the pampas, making decisions about what to plant and when to plant it, we might have an environmental model that the agents can access through the particular coordinates they are at, that gives it how much rainfall occurs in a particular time, as well as a hydrology model as part of the environment, which determines what the water table height is that the agents can access during the simulation. Okay, and fourth, some kind of simulation model mechanism. And this really steps the model forward by activating the agent interactions and managing updates to the agents and their environmental states. These functions are encapsulated in programs that basically comprise the recursive system that I'm going to talk about. Okay, so as I said, I've been on a quest to define the simplest possible agent-based model representation that applies to all agent-based models. Simple is good because it's simple. It would be simple to understand, it's simple to build models, and simple to communicate what the model does. And kind of a standardization is what I'm looking for. So in simulation modeling parlance, an agent-based model is a discrete time-step simulation model. And at each time step, agents execute behaviors, which can include things like making decisions. Agents interact with other agents, which results in agents updating their state, typically. And then agents interact with what I call the modeled environment. It's the environment that's included in the model that the agents can interact with. And these are what's in the environment is outside of the agents. So basically, this flow chart is my distillation of the simplest possible agent-based model representation. It's universally applicable to all agent-based models. Essentially, there's 2 parts. There's a create part, and then there's an update part. And there's basically, in this representation, there's 2 loops. There's an inner loop, which is the agent loop that basically updates all of the agents in the model at a given time step. And then there's an outer loop that updates the time steps themselves. Okay, so what my goal was to simplify this kind of representation into one single recursive equation. And I did that, and I want to show you how I did that. So a recursive system is represented in the Wolfram language by a single line expression. This expression includes 3 composite functions representing agents, interaction groups, and the environment in my use of the recursive system. So I use a fold list to recursively update agent states over a range of time steps. And doing that is the simulation model mechanism, as I call it. And this recursive form essentially encapsulates the full functioning of any agent-based model. It was pleasantly surprising to me that the recursive system form is expressive enough to represent the most general form of any agent-based model. So here's how I did that. Okay, so basically, to get the ABM rolling, we just need to initialize the agents and the environment. We define a create agents program and a create environments program to do this, which tend to be very simple programs that supply appropriate parameters. So basically, this is the code that does that initialization. And it's wrapped up in a function called initialize ABM. But the key point here is that what comes out of that, this code, are agents and the environment. Okay, we could get the agents in the environment in other ways. You know, we might read data indirectly, things like that. But I'm struck by the simplicity of how simple it is to do that. I don't show the routines here for creating the environment or creating the agents, but basically the idea is we define some parameters that are needed to create the environment. And in this example that I have, there are only 2 parameters. And this is the SIR compartmental model, basically, that you may or may not be familiar with. But there's a probability of infection, which is essentially the beta parameter in the SIR model. And there's a mean duration of the infection, which is basically the gamma parameter in the model. So it's a simple model with these 2 parameters. The reason that these parameters are in the environment is that it's possible over time that when we're doing the simulation, we want to update the environment. And these parameters, we supplied new parameters to be updated at that time. So very briefly, how this played, I did a lot of COVID modeling myself, agent-based modeling, and it really had quite an impact. But one of the factors in COVID was the infectivity of the SARS-CoV-2 virus. And there was a baseline infectivity rate that was estimated. But later, about a year later or so, there was a mutation that occurred, and the new strain of the virus, called the Delta strain, was 50% more effective than the original strain. So anyway, I was talking about this is the equivalent recursive system, right? So this is the punchline for the whole talk. And basically, as I had said, this is a fold list that is done over the agents and the time steps, which I've set it 1 to 28. And basically how it works is that previously I had defined the initial agents and defined the initial environment. And so this update environment function takes the environment as it was in the previous time step and takes the current time step and the current set of agents and returns the new environment right there. And then secondly, the agents are updated in the groups in which they occur, which happens to be this function that creates the groups each step. There's a lot of recursion going on here, so it's obviously certainly confusing to really figure out maybe the first time through it. But basically, I'm taking all of the agents down here, which is number one, or pound sign one, and I'm creating groups from those agents. So I'm sending each group to be number one up here, which is used to update the environment, update all the agent states in the groups, and in the end returns a new expression for the agents. So this whole thing here essentially updates all the agents at the step. And then what I'm doing is to return this log run function, which essentially takes all of the agents at each step and just puts it into the log run expression. So anyway, this is the highly documented version because it's hard to it's kind of hard to figure out, but I think the beauty is this is one single statement here with these basically three functions that I'm not showing you, but are very simple functions for updating things. And so, I do a check down here to see that in the log run function, we have 29 records of the agents, because it's 29 steps, basically, including the initialization plus 28. And we had 100 agents in this run. And so each one has 100. And this is basically what one of the logs look like. Everybody is, and at the final step, actually, everybody is in the R state because everybody's recovered. So I can move on here to explain that a little better. By the way, if you take out all the comments and everything, the statement is maybe less intimidating to decipher as to what's going on. But yeah, so this is basically the one-liner. It's a long line, but it actually is kind of pretty amazing. By the way, so anyway, if I analyze the results, this is a typical kind of output for the SRI ABM. I simulated 100 agents. I have actually using the same, function program. I've simulated the 2.7 million agents in Chicago, of the real city, and it works the same way. So anyway, so what's shown here, I should explain. We begin, the blue is the number of susceptibles to begin the simulation. That drops very quickly as people are, having contact with agents, having contact with each other and affecting other agents. So the number of infected agents climbs to like this typical peak, and then it tails off as most of the agents are actually infected. And then finally, this green line is the recovered number of people recovered. So my point is, this is exactly the typical kind of output you'd expect from an SIR compartmental differential equation model that uses three equations. But we've done it here with individual agents, and we've done it with this recursive equation. So in conclusion, think this is really amazing. This result has enormous practical applications for me in my work, because I build agent-based models all the time in various domains. And to have this kind of single equation power is probably, both very powerful, but also very easy to explain people as to at least what it's doing, so that they feel comfortable with agent-based modeling as not being such an intimidating thing for which you have to learn all kinds of stuff to do. Anyway, I see our time is up, so I thank you very much for listening. I don't know if we have any time for questions, but I'm happy to answer anything if it happens to come up on the or in the chat. Thank you very much.
Charles, you have one question in the Q&A tab.
Q&A tab. Okay, so the Q&A tab is located. Can you give me a hint on the Q&A tab?
I can read the question for you if you'd like.
Sure. Oh, there's the Q&A. Sorry. Okay. Have you found Wolfram? Okay, here, have you found Wolfram length performance to be a limitation in your ABM work? In my ABM work, I moved to Julia. Well, that's a very good question. I have also implemented this in Julia as well as Python. And I would, of course, Julia is going to be faster, but it's a question of how fast you really need your performance. If you want to do the program in Julia, go ahead. I found Julia is very hard to program in. You got to program it every day. But one thing that I'll just say that I found that we're working on here in my research at Argonne is in kind of reformulating agent-based models to run on GPUs. And basically, it's a lot of reformulation of the basic problem, as matrices and functions on matrices, right? So I have not, the final answer is in my ABM work, I've been able to take my Wolfram code and make it a lot more efficient by some of the techniques that I've used for, like, in particular, agent state updating, things like that. I have not found it to be a limitation in the sense that I've had to move to another language. No, but it's taken a lot of fiddling to squeeze out the absolute maximum efficiency out of the Wolfram way to do coding. And I've had several great talks with people at Wolfram on this subject. Usually it's at the Wolfram at the conference in the past. So that's my answer. Okay, well, I know it's time for the keynote by Stephen. So I'm just going to log off here and say thank you very much for watching.